Number 7. Yeah. All right. Data representation. When we are given a sequence of data points, next, we want to do the modeling. We want to create a good model to represent the given data. Why we want to model the given data? Because the given data, a sequence of scattered points. Now, the scattered points, there is no good representation for it. If you do not do the modeling, so then it is very hard to apply different tools on it for data processing. So before you can apply some powerful tools, you need to provide a good model to represent your data. So that is the motivation. Now, all right. So here, the goal, we need to apply various mathematical tools on data points. Here, example, derivatives, integrals, and other than that, there are many different transforms. Think about that, transform, like Fourier transforms, right? Think about some advanced, powerful, advanced data processing tools. Think about Fourier transforms. Transform, yeah. This is a very famous transform in data processing, Fourier transform. Yeah. And similarly, there are many other different transforms. Without good modeling, then you cannot apply all these powerful tools. Okay, yeah. All right. So now, at the modeling step, we need to find a good continuous function, f of t, such that f of xj equals yj. Yeah. This relationship, this is one way for, so this is just the one way, all right? Yeah. This is the one of the ways. There are many different ways. Yeah. This is our first way. Yeah. Let me talk about this way. Let me elaborate this way next. Yeah. Okay. Yeah. So my next concept I like to talk about, I try to elaborate this way. Okay. Yeah. Elaborate this way. Yeah. So my next step. All right. Item number 8. Another important concept called the data interpolation concept. Data interpolation concept. Okay, yeah. One way, yeah. One important way. Yeah. First, let me draw this graph to show you the data interpolation idea. So given a sequence of data points on a plane, yeah. Here we just consider 2D case. Yeah. We can generalize the idea to 3D and high dimensional also possible, right? Because your data points could be given there is a case, the data points in high dimension. High dimension. That's possible. Yeah. Hard to imagine, but it's possible. Yeah. All right. So here, 2D case. Data interpolation, we like to find continuous function. Continuous function, we use continuous C. Yeah. C on some interval. Yeah. One situation, real axis, real numbers. This R means the real numbers. Continuous functions on real numbers. Yeah. So the function interpolation. Yeah. Passing through all the data points. Okay. Yeah. So let's say that this function is f of t. Okay. Yeah. A typical data point x, j, y, j. Okay. Fine. So we write the representation is like this. Find a function f of t in this set, continuous function set, C of R, continuous function set. Okay, yeah. This means the set of continuous functions. All right, yeah. Find continuous function such that f of xj equals yj for this j, remember our data points, the subscript in this range, starting from 0 and the last one n, from 0 to n. And in this property, so we give it a name. This property is called interpolation property. Interpolation property. And this representation, this representation we call this representation, that's called, we represent the data by interpolation. Yeah, okay, the concept. Yeah. All right. So here, our modeling function, this f of t, the model function. Okay, yeah. Here we require the property continuous property. Continuous property, all right? But this requirement may not be good enough. So this property may not be good enough. Why? Because when a function to be a continuous, there are so many different ways to choose from. Okay, yeah. So look at the simple example here. Yeah. So here, let me draw a continuous function here. Okay, yeah. Suppose on a plane, let me draw a continuous function like that. Okay, a lot of wiggles. Okay, it is continuous. All right, yeah, but it's not very smooth. Okay, yeah, yeah. So this continuous function, not smooth. So this example tells us when you have some freedom to choose in the continuous function set, you want to choose good function. You want to, how to describe that good property? Smoothness is one, right? The smoothness is some desirable property we like to have. Okay, yeah, yeah, yeah. So, so we need to, try to describe a good continuous function, convenient to use, continuous function with good properties. So our next step, yeah. So what do we need to do? So actually, yeah, let's set our new goal. Okay, our new goal. Find a continuous function with good properties. Right? Yeah. Okay. What good properties? Yeah, let me just list a few. Yeah. First, smooth. But smooth. How do you describe the smoothness, right? How to how to describe the smoothness? How to describe the smoothness? Yeah. All right. Then in calculus, we have a way to describe smoothness. Yeah. Using derivative. Okay. Derivatives. First, second, third derivative. Okay. Yeah. The higher order the derivative this function has, the smoother we call this function. Yeah. So let me write this way. The higher order of derivative this function has the smoother the function. Okay, yeah. All right, so we use that derivative concept. So we can get this property. That's one property we like to have. Another property we like to have, okay, easy evaluation. Yeah, because we need to find a function value let's say f of t. When you plug in a number, a value for your variable t, you need to find the function value. So that's the evaluation. When we do function evaluation, we want to make sure the operation is relatively simple. Yeah. We don't want to do a very complicated evaluation. Okay? If your function is defined in a very complex way, so you need to do a lot of extremely complicated operations. We don't like to choose those functions. Okay? Yeah, too much computing work. We want to make our function as simple as possible. This means, yeah, so make the function as simple as possible. Right? Yeah. Then when we manipulate this function, very easy, a lot of operations when we apply on this function, very easy, very fast. Yeah. All right. Yeah. So that's another property. Yeah. Second property. Another one, it should be very flexible. Right? Because you cannot expect your data in any specific form. Your data is pretty much arbitrarily given. Yeah. So your function, you can represent arbitrary given data, okay, with any form. Yeah. The form could be, up and down, a lot of fluctuations, you can always represent your data well, okay? So the function you choose should be very flexible, representing all the shapes. Okay, yeah. So this is another property we like to have, yeah. But this one, you may not be very familiar with this property, yeah. But I will elaborate, I will elaborate this later, okay? Later, I will spend quite some time to elaborate later. All right, yeah, flexible, all right, yeah. Then another, yeah. So here I just list some basic properties. So I cannot list all of them, okay? Yeah. I just list some, properties that I can think of. All right, yeah. So let me put another good property we like to have for this continuous function. All right. Help put the computation errors under control. What's that? Okay. Yeah. What's that? Computation errors. Yeah. Later I will also elaborate, but here let me explain a little bit. Computation errors. When we do computation, we use computers, right? Yeah. We always use computer to do the computation. We write programs. But when you use computers, how does computer represent a number? Floating point number, double, right? We use floating point, we use double, yeah, with certain precision. But no matter how you represent a number in a computer, there is some error, right? You cannot say your data representation is always precise. You have error. But when you do computation in a computer, think about your errors could be accumulated, yeah? Because you need to do operations many times. Operation 1, operation 2, operation 3. Each operation you have some error. So the error could be built up, accumulated, and the error could grow bigger and bigger. Think about that. All right. If your function is not good, your function could enlarge the computation errors. Later, I will show you what's the meaning, enlarge the computation errors. Okay, later you will see some simple examples. You can easily see, how big is the impact if you choose some bad function. The computation errors could be out of control. Out of control. All right. Yes. Yeah. Yeah. You will see that simple example. Okay. Yeah. All right. So here you can see. Yeah. At this point, it may not be easy to find a good continuous function, right? Yeah. Think about it. Here. I just give you 4 properties. Yeah. It may not be that easy. Yeah. But we will get there. All right. We will get there. Yeah. Yeah. Good continuous function. Yeah. All right. Yeah. Next, let me give you a first example. First simple example for data interpolation. Number 9. Okay. The simplest data interpolation. It's called a linear interpolation. Linear interpolation, here we put it, it's the simplest. Interpolation, yeah. So you can easily imagine what kind of interpolation we need for this one. Okay, yeah. A sequence of data points. All right, yeah. Linear, yeah. Draw line segments between any two adjacent data points. Straight line segment. All right. Is that simple? Is that simple? Right? Is that simple? All right. Okay. Linear interpolation. If you check the properties we have, first it's continuous, right? Yeah. Yeah. First, obviously, it is continuous. Yeah. All right. Yeah. Second, it's simple, right? Yeah. Easy evaluation, right? Yeah. Flexible or not? Yeah, flexible may not be that good. Yeah, we cannot say it's very flexible. Yeah. Yeah, we can say, yeah. And then error control, it's good. Error control. Yeah, the error will not be, build up quickly, yeah. But the biggest drawback here, this one, not smooth. Yeah. It is not smooth. Yeah, because look at each point, there is a corner, right? So you can see corner. What's the corner means? Each corner, the corner means the derivative does not exist. That's not good. The derivative does not exist. Okay? Yeah. But it is simple. We cannot say it is useless. It is useful for some, special situations. Still useful. Yeah. Yeah. All right. Yeah. But this is a simple one. But you cannot expect this representation is good for most of the operation. You cannot expect that. Okay. Only for probably small number of applications. Yeah. So this representation is good enough. Yeah. But for most of the applications, real world applications, we should find much better representations than this one. Okay, yeah. All right. Next, yeah, let me give you another type of data representation, a different type, different than the one we're talking about. So number 10, we call it data approximation type representation. Okay, data approximation type. Okay, type of representation. So what's that? Data approximation. Here, let me just draw a simple graph so you can see its meaning. Yeah. First, from the English word, you can guess the meaning a little bit. Yeah. But let me explain a little more. Yeah. Think about the data set, data points given could be, like that, very irregular, right? Wiggles a lot. Okay, yeah. you know, like stock market data, right? Yeah, so a lot of real world data could be like this one. Okay, yeah, and usually for data like this, it is hard. Yeah, the writing is slow. Yeah, it is hard to use a smooth function. Yeah, yeah, I think yeah, the response time is not good now. Yeah. Hmm. 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 Yeah. Move function. Hmm. All right. Yeah. To interpolate it. Yeah. Look at the, interpolation property. Interpolate it. Yeah, so slow. Next time I need to restart my computer, before the class. Yeah. I just finished teaching a class, 1 hour ago. Probably, my computer is not in the, fast mode. Yeah. Then a better way to represent this data, we do not need to interpolate it. We do not need to interpolate it. We approximate it. Look at this way. We use a smooth function to pass through to approximate the point. We do not have to pass through all the data points. All right. We use a smooth function to approximate the function. How about that? And the function we can make it very smooth. We just approximate the given data. So this approximation idea. Okay. So this is another type of representation. This representation has some good properties, yeah, because this representation we can remove a lot of noise. Look at that. Because think about the data could contain noise, right? Yeah. So the data could contain so bad. Contain, yeah, noise. Okay, yep. But with approximation, we can remove a lot of noise because we do smoothing here. What do we basically do? We smooth the given data. We do smoothing with approximation. Okay, so remove a lot of noise. Okay? All right. So this representation also useful. Okay. So here we do not say which one is better, right? Here I give you two different data representations. One data interpolation, another data approximation. You cannot say one is better than the other. Each one has its own good properties. Yeah. It depends on your applications. For some applications, you may need to use that interpolation type representation. And for some other applications, you may need to use the approximation type data representation. All right, yeah. So these two are two basic data representation types. Yeah, yeah. Today, yeah, because the handwriting becomes extremely slow. Yeah, so let me stop here. Yeah, next time before our meeting, I try to restart my computer. Yeah, so I think if I restart my computer before the meeting, my handwriting should be very responsive. Yeah, not this slow. Okay, it is too slow. Yeah. All right, so let us try to digest, try to think about these concepts, try to digest a little bit. Yeah. Later, I will give you how to do data representations, approximation, and interpolation with good functions. Later, I will go there. Okay. Yeah. All right.
Sure, Professor. So
Yeah.
I have a question. So mostly in the first class and the second class, we are mostly looking at the mathematical format, right? So how do we implement that in real time?
Real time. Oh, you asked me first, second, what?
In the first and second class, majority of things we did in mathematical format, right?
Yes. Yeah. Yeah. Math formula. So you asked me how to implement
In real-time scenarios.
real time. Yeah. Real time, our computer power is pretty good. PC, even we use Python, it should be very fast. Yeah. But
Okay.
regarding the, real time data processing, then another big issue you need to consider, that is algorithms. If your algorithms is good or not. Okay. So here, algorithm. All right. All right. So we will get there. Okay. If you choose some bad algorithms, you cannot get real time. You need to wait a few hours to see your, processing result. But if you choose a good algorithm, you can get the same result in fractional seconds. Yeah, extremely fast. Yeah, and in this class, I will give you a chance to do comparison. Okay, so what I'm talking about, I will give you an example, ask you to use current existing algorithm that is not very good, and then after that, I will give you a new, the new one I just developed, a new one. We can do the data interpolation real time. All right. So your
Okay.
question, very good, but I will give